Cams on everyone. Let's start off.
Bluetooth mode.
Great. Let's go ahead. The last thing that we did, we got an equation for this Doppler thing with the signs. So just let me put down this thing again. So first thing, these formulas you're using, right? They're valid when the source, observer, and the wind are moving along the same line with constant velocities. And so that was one. Next thing, just give me a minute. Yeah. Next thing. When you're solving this, never use relative velocities. So even though if you see, right, when we started the definition, we said if there's a relative velocity, there's a Doppler effect. But if you observe, whenever the source is moving, the wavelength was changing, that was affecting the denominator. When observer was moving, it was changing the apparent speed and it was affecting the numerator. So they're not actually affecting the same thing. So you should never use relative velocities, meaning you should not say, I'll stop the object and they'll solve the problem. All these velocities must be in the ground frame. So that is V naught. Vs are with respect to ground. Then your formula becomes F apparent C plus or minus wind plus or minus V observer by, last time we saw, when it is plus and minus for the wind, if the wind is blowing from the source to the observer, means if it is supporting the sound ka speed, then it is plus. If it is opposing, then it is minus. Now there is something more here. You can also write this thing as C plus or minus W by V naught by C plus or minus W plus or minus Vs by F. So this is nothing but a C apparent by lambda apparent. Everyone knows how to find F apparent, but sometimes they'll ask you find lambda apparent. And you need not do anything new. It is there in this only. You just bring that F down and you get this lambda apparent. And you can clearly see lambda depends only on the source ka speed. It doesn't depend on the observer ka speed. All clear so far? No. There is one more level to this, but we will see that later on. Let's do some problems before going ahead. You should get used to the formula. Once you got used to it, it is pretty easy. So let's do one question. This will cover all the cases. Let's say we have a vehicle. The vehicle is going with a speed of 10 meters per second. On the vehicle at the middle, there is a siren, which is generating a frequency 500 hertz. We have an observer here, A, who is running forward with 5 meters per second. Let's say we have an observer B who is running towards the vehicle with 5 meters per second. Let's say we have a person C who is coming towards the vehicle with 5 meters per second. We have an observer D who is running away from the vehicle 5 meters per second. We have an observer E who is sitting in the front of the vehicle. And we have an observer F who is sitting on the last seat in the vehicle. So there are total 6 people here. A and F are sitting in the vehicle. You can say it's an open window, okay? That doors are open, sound can enter inside, all that stuff. These are all the 6 possibilities you can have. Yeah, if you do this, we will know how to use the formula. So find F apparent and lambda apparent and C apparent for all 6 of them. Take a minute. I'll show you one and then I'll give you more time for the remaining. But let's give it a try. You got this. You understood the formula. Okay, let me show you one. Let's see the first one. Then let's talk about A first. Wait, I forgot one more thing. There is one more thing here. There is a wind also blowing here. Let's say wind gust speed is also something like 3 meters per second. There is a wind also. I forgot to give. Yeah, that will take care of everything now. Now try. Give a little more time and then I'll show you for A in a minute. Again, no need to simplify. Don't worry about getting the numbers. Just be careful when it is plus and when it is minus. That's the main catch. Okay. Let's see for A. So when you ask for A, again, listen to the formula carefully. F apparent, speed of sound C. Now, what is the wind doing? Look at this. For A, if you look at M, the sound is going from left to right. And the wind is also going in the same direction. So it will be plus W. Right? And what is the observer doing? The observer is trying to run away from the source. See, I don't care whether he's actually going away or not. The vehicle speed is 10. Definitely they're getting closer. We're not interested in that. We just want to know what is the guy doing to do. He's trying to run away. So frequency should decrease. So minus VA by C plus W. What is the vehicle trying to do? Vehicle is trying to go towards the observer. It should increase the frequency, but it is in the denominator. So minus VS into F. Check. You can put the numbers and you'll get the answer there. Now, what is C apparent here? You can just bring that F down and we'll get C plus W minus VA by C plus W minus VS by F. This is your lambda apparent and the numerator is your C apparent. Clear everyone what we did? So it's all about finding out which is plus and which is minus. When you're adding plus W, right? Remember you're adding the W to C actually. It is becoming C plus W. I'll just show you for B also. So B guy is coming this way. So F apparent per B, C, the sound is going from left to right. Wind is also going left to right plus W. Observer is trying to go towards, so VB. Source is also coming towards C plus W minus VS into F. Yeah, same story. You got the answer. Now, can you try for CDEF? I'll give you a minute. Bring that F down, you'll get C apparent. V source. Vs is V source. Okay, let's see for C and D. Now for C, if you ask me to solve the problem, look at the wind, how it is blowing now. Wind is going left to right, but the sound is going from right to left. So the wind is actually opposing the sound. So F apparent for C will be speed of sound minus W. It is subtracting. What is the observer trying to do? Observer is trying to go towards the source, so frequency should increase, plus Vc. C minus W. What is the source trying to do? Source is trying to run away from the observer, so frequency should decrease. But you're in the denominator, plus Vs into F. That's how you always see. That is how you get plus and minus signs. What about D? C minus W minus Vd by C minus W plus Vs into F. Let's try for E and F. E and F are interesting ones. E and F will be good theoretical questions. They will make a statement like this. Since relative velocity for E and F is zero with respect to the source, the frequency doesn't change. They'll give a statement like this. Listen to the statement. Since the relative velocity between E and the source is zero, he will hear the same frequency. What do you think about this statement? Let's calculate for E and F. Let's see. Now, like I said, we never care about the relative velocities. You always have to take the velocity in the ground frame. Meaning you can assume he is standing outside the truck and he is also running with the same speed 10 meter per second. You can treat him like that. And sitting in the front and sitting at the back, what changes basically? Let's see. Great. Listen. That statement is a wrong statement, getting it? So now if you ask E to solve the problem, this is what E will say. Now E is sitting in the front. Assume the guy E is as good as a person beside and he's going with the same speed as 10 meter per second. You can treat E like that. The equation doesn't care whether you're sitting inside or you're running outside. So it is as good as that. So now when you write it, we can clearly see the sound is going ahead for this person. So you're sitting in the front seat. So F apparent will be C, the wind is supporting you, plus W. Observer is trying to run away, so VE by C plus W. Source is trying to come towards you, so minus Vs into F. Now here VE is equal to Vs. We get F apparent is equal to F. But if you actually see the reason, the reason why it is getting cancelled out is not because the relative velocity is zero. The C apparent is changing, the wavelength is changing, but the ratio is not changing. So he will see the speed of sound is different. He will see the wavelength is different. This is where most people goof up. They think the frequency is same, wavelength is also same. Not necessary. He will actually think the wavelength has decreased or increased. At the same thing, if you ask for F to solve the problem, you can do the same thing. You can just take this guy F and make him run outside with the same speed. So F will write F apparent C minus W because sound is going backward and he's trying to go towards, so frequency should increase, plus Vd by C minus W, it's going to away, so Vs into F. Again, if you solve this, you'll end up with F apparent is equal to F. Frequency is same, but lambda apparent is not same. Is this making sense, everyone? Did you see? Their lambda apparent is completely different. Because the guy in front of the source will think waves are getting compressed. The guy behind the source will think waves are getting expanded. So be careful with that statement. Since the relative velocity is zero, the apparent frequency is zero. That statement is a blunder. Relative velocity has nothing to do with the problem. When both are going with the same velocity, the C apparent is changing, lambda apparent is changing, but that ratio is not changing. So it is working out. That's it. There is no reason it has to do with relative motion. Is that making sense, everyone? So sitting in the front of the bus and the back of the bus, if your siren is in the middle, they actually see different wavelengths. Let me show you how. It must be in wave optics. This is called a ripple tank. Look at the setup there. The setup, right? We have a glass panel. On top of it, there is a water. And you have the left side, you can see that big arm, that is an oscillator. So there is a needle there, which is touching the water surface. So when you're vibrating this, the needle is continuously hitting the water surface. So when you're hitting the water surface, you get ripples on that glass plate. And at the bottom of the glass plate, you kept a light. So that light is shining on the glass plate and you're getting a reflection. To see how it looks. We are actually looking at the reflection. So you have a light at the bottom. Can you see the reflections on the ceiling? So when the water is hitting, the needle is hitting the water surface, you're getting ripples here. And when you put a light at the bottom, you get a shadow on the ceiling. We capture this shadow on the ceiling and then we project it on a screen. We have a camera set up and everything. And that's what we are looking at. Then look at this picture here. Can you clearly see the wave, how it is traveling? So there is a needle which is hitting at one particular spot and the waves are continuously traveling. The distance between two waves is lambda. So this is what I was drawing, wave one, wave two, wave three, and all this. So yeah, kind of like that. So now if you increase the frequency or decrease the frequency, meaning if you make it oscillate slower or faster, you can clearly see wavelength changes. So they decrease the frequency. Now look at the size of the wave. Like the difference is bigger. Wavelength has increased. If you oscillate faster, the wavelengths will decrease. So there we have created a source there. Now this is oscillating faster. Can you see this become much closer? They're more tight. Now we got a source. So this is a source. Now if you're moving this is a Doppler, isn't it? When a source is moving, the wavelength gets messed up. Now see, when he's moving, you can clearly see the waves on the top are getting compressed. The waves at the bottom are expanding. Maybe it's not that clear. He will move fast. Then you can, I think, in this picture you can clearly see. Can you see now? The waves at the bottom are much closer. The waves on the top are expanding. So if anyone is standing in front of the source, they will think the wavelength is decreased, and anyone who's standing behind will think wavelength is increased. This is what we have done last class. Now, if you move it fast, then the change is more. There you can clearly see here. Can you see the waves at the top, how they're getting pretty compressed there? And the waves at the back are getting expanded. There, this phenomena, right, of the wavelength changing, this will lead to change in frequency, and this is what we call as Doppler effect. Now, if you can move really fast enough, meaning if you move the source faster than the speed of the wave, then you can clearly see the compressions here. Then what will happen? These waves, right, they will start piling up on the source, and you'll get a shock wave. You must have heard that sound barrier karke. When you go faster than speed of sound, it get a shock wave. So there he's going fast. Yeah, there. When he goes fast, can you see how is that? All the waves are getting accumulated at the front, and you get a shock wave. That's about the Doppler. So I hope you can see the Doppler. You know, where else you can see the Doppler? Um, when you, if you ever seen this, you know, F1 racing and everything, those cars, right, they make a sound like this. Listen to this sound. I don't know whether it is audible. See that starting a sound, okay, when they're coming towards you. Can you see that sound? It is going, decreasing. So when they're coming towards you, you have high frequency. When they go away from you, you have low frequency. Frequency decreases. So so you must have heard that sound. Like that's your thing there. Oh wait, I think I didn't share you that video. I just wait, my mistake. Listen to this sound. Is that audible? Did you hear that sound? How the frequency just dropped? Like I'll post this as a small video. You can check it out. There, that is the thing. So be careful. Relative velocity has nothing to do with your Doppler thing. Let's see one more question. But this question will cover maximum, like, you know, if you understood that, most of the easy questions will be done. So we have a vehicle here. We have a driver here. The car is going with a speed V. We got a siren here, frequency F. There is a wall here. The wall is also moving with the speed of U. C is the speed of sound. So the car is going towards the wall, and the wall is also moving towards the observer there. So first thing, find the frequency and the wavelength seen by the wall. So the sound will come and hit the wall. It will think the frequency is different and wavelength is different. After hitting the wall, you get an echo. So this echo will travel back to the driver again. Find frequency and wavelength heard by the driver of the echo heard by the driver. Find the number of beats heard by the driver. Now the driver will hear actually two different frequencies. This is how they actually use the speed guns. If you ever heard that word, cricket, if you see, right, how do they find the speed of the ball? Or same thing, you know, when vehicles are overspeeding, the cameras which they have, they actually use kind of Doppler radars, everything. They work all on this principle only. You know how fast it is going based on this. You're sending a signal, it hits and comes back, and you detect it. Let's give it a try. It doesn't matter, right? He's in the car. You have to do double Doppler. Basically, first the car is the source, wall is the observer. Then whatever frequency the wall will listen, that only it will reflect. So then wall becomes the source and car becomes the observer. Do give it a try, everyone. I'll give you 2 minutes. It's a good one. If you do this, I think at a mains level, bits level, mains is not there, but at a bits level, they ask you questions, you are covered. Hmm. Let's see. Let's see. So whatever sound is coming here, so first this guy, wall will be the observer, and this will be the source. So this will hear a frequency F1, which is C. Wind is not there. Uh, Observer is doing what? Going towards the source, so plus U. Source is also going toward the source, minus V into F. You can bring that down, and that would be C plus U by C minus V by F. That is your lambda apparent. So if you see, lambda apparent always depends only on the source velocity. Now, whatever sound you get, now you are reflecting it back. That frequency will be F1. Now, this is the source, and this guy is the observer. And this guy will hear F2, which is C. Observer is going towards the source plus V. Source is going minus U. Be careful into F1. So what is lambda apparent here? You should not simplify it. You should bring it down here only. This is your lambda apparent. Now simplify if you want. Now this will be C plus V by C minus U. F1 will be C plus U by C minus V into F. That is the frequency we'll hear. What is the number of beats? Now the driver will hear two frequencies. One frequency directly from the vehicle, which will be F. The other frequency is F2. That is the echo. He will never hear F1. The driver does not know what is F1. F1 only will become F2. Is this clear, everyone? So first you have to take the wall as an observer, car as a source. Whatever frequency the wall will hear, that only will get reflected. Now wall will become the source and the car becomes an observer. You have to apply Doppler back to back. Pretty important question, standard one. Any doubts on this? Clear how we did this? Anyone confused with anything here? Next one. Let's say we have water here. have a source here, frequency f, and the source is going up with, let's say, V3. Source is going down with V1. The water level is going up with V2. And we have an observer here, and this guy is also coming down with V3. The speed of sound in air is C. The speed of sound in water is 4C. And this is the thing. See, now the observer and the source are in two different mediums. The speed of sound is different. Now, what will the observer here? Find F apparent and lambda apparent of the seen by the observer. Now, you can't apply the formula directly. Let's see what will you do here. Think, I'll give 2-3 minutes. This is another good variation. Observer and source are in two different mediums. V1 and all V को क्यों ऐसा V में देंगे तो क्या करोगे? करो. Point is that only to put it in variables. Samyak did get something. Looks right. Let's see. I'll give another 30-40 seconds and I'll show you. Let's see. Now, the thing here is you can apply the Doppler only when you're in the same medium because the speed of sound, everything will change. So what we will do here, consider the interface, right? So the sound will first go and hit the interface. So the interface is the observer and this is the source. So the interface will hear a sound F1, which is speed of sound 4C. So observer is trying to go away from you, so minus V2 by 4C. Source is also trying to go away from you plus V1 into F. This is the frequency is heard by the interface. Then whatever sound the interface will hear, the same sound will go out. Remember, the frequency does not change when you go from one medium to another medium. Now this will become a source and this guy becomes an observer. So you have to apply Doppler separately for both the mediums. So first you find whatever is the frequency heard by the interface. That becomes the source. The same frequency will get out of the water and goes into the air. Now this propagates. Now this guy will write F2. Now the speed of sound is C. The observer is trying to go towards, so plus V3. Source is also coming towards, so minus V2 into F1. Is this making sense, everyone? So instead of a wall, we have a water surface. So you will apply Doppler from the source to the water surface and water surface to this thing. And what is lambda apparent? Lambda apparent is C minus V2 by F1. That's it. So if your observer and source are not in the same medium, then you treat the interface as a new observer. Let him hear a frequency, and that frequency will get out because frequency does not change when you go from one medium to another medium. Any doubts on this? Clear? Now that looks easy. So kind of, if you see, it has a vibes of the similar to the previous problem. The only thing, the speed of sound is different. So just be careful with that. Next thing. Let's say we have a source, frequency f, and let's say this is a constant acceleration. Now your source is accelerating. So initially at rest, the siren starts at t0, and the vehicle is initially at rest. An observer is standing here, and the observer is also at rest. Now, find the frequency of the first sound the observer hears. Now, we can't find as function of time t, it gets messed up. But the first sound that this guy will hear, what is the frequency of that sound? Find the frequency of the first sound the observer hears. Let's see how will you approach it. Now, you can't use those formulas because those formulas are derived when the velocity is constant. You have to go back to the derivation. You need to see how we even derived that frequency. Think for a minute. Let's see. Now, if you go back to the derivation, this is how we did. We said at t0, you release the first sound wave. Time period is 1 by f. This is the time interval between two pulses. By the time you release the second pulse, the source must have moved a little ahead. This distance must be half a capital T square. This is where you're releasing your second pulse, but the first pulse must have already gone ahead. And this distance must be Ct. This will be your lambda apparent. So this guy will think the wavelength has become Ct minus half AT square. If you remember, this is how we derived that. And then you're done. F apparent will be C by lambda apparent, which is C by F minus A by 2F square. You can simplify it. That's your answer. Clear? Now you can't find as, function of time t and all, because as you get closer and closer, the distances will keep changing. It can be done, but it'll keep changing. Finding the initial part was the easy one. Clear with these variations, everyone. The next thing. Now, if you see here, everything was going in a line. What if your source and observer are not along the same line? If source and observer are moving at angles. So let's say something like this. Let's say this is the frequency, t is 0. This is the source, which is going with some speed vs. This guy is an observer. He is going with v0, and this is equal to t0. Now, listen to the statement here. The moment the sound is released, do you think this person will hear that sound? By the time the sound goes from here to here, won't you think the observer must have gone ahead? So the observer will not be at the same place when the sound is reaching. So that means after time t, when the observer hears the sound, this is how the scenario will look like. The source must have moved here. The observer must have moved here. That means this guy will hear the sound which was released in this line. So the sound which was released to this position, that will reach him. So this is your V0. So when you take angles here, if you take this angle to be, let's say, some theta 1, and if this angle to be theta 2, the velocities must be components. So the formula is still the same. F apparent, which is C plus or minus wind plus or minus V observer, by C plus or minus wind plus or minus Vs into F. So the important thing is this. So the wind gust speed, V0 and Vs are components along the line joining the source when sound is released. So source is important when the sound is released. After that, where it goes, we don't care. So if I mark the points, let's call this point as B. Let's call this point as B dash. Let's call this point as A, and let's this point as A dash. So that is point B. That is where the sound is released. And observer when sound is received. Observer ka initial position is useless. His velocity ka component is important when he is receiving the sound. Right? When sound is received. And that is A dash. So you're actually taking 2 points at different times. So that will be line A dash B. So in this thing, velocity of observer will be whatever is that velocity. So I'll do one thing, I'll call it V1. So velocity of observer will be V1 cos theta 1. Velocity of source will be V2 cos theta 2. This is important, everyone. This is the final level of Doppler. If you're not going along the same line, then you have to take components. Which components? Should join the line when the sound is released, and the observer when the sound is received. You're looking at 2 points which occurred at two different times, and then it works. Clear with this? There are the three levels: without wind, with the wind, at angles. Now let's see a few questions on this. We have an observer who is standing at the origin. We have a frequency f, and this is traveling with phi. So this is traveling above the x-axis at a certain height from minus infinity to plus infinity. Source moves at a height from minus infinity to plus infinity with constant speed. So when the sound is being received with this guy, plot the apparent frequency versus the x coordinate of the source. So at a particular x coordinate, if the sound is released, what is that apparent frequency when it receives this guy? Yeah, there will be a time lag. We are not interested in that. Approximately, we have to draw x coordinate of the source when sound is released. Yeah, you'll get four options. You have to eliminate them. But let's try to draw roughly. How will you draw this thing? So think of like this: an aeroplane is flying in the sky, and you're watching there. So how will the frequency look like? Can you put those values roughly, Nadia? Uh, Theoretical, yeah, the graph will look like that. So they can also give options like this, huh? The frequency will increase and decrease. The frequency will always increase. Frequency will always decrease. Frequency will decrease and increase. It's a चार option they can make it. I'll go 30, 40 seconds. I'll show you. Let's see. Now let's put a picture here. Now try to understand. When this guy is coming closer, we are interested in the component. So we have to take this component here. This is theta, so this will be v cos theta. When you're exactly on top of this person, the velocity is completely perpendicular. So there is no component. So at this point, theta is 90 and v cos theta is 0. That means when you're exactly on top of your head, there is no velocity towards the observer. The f apparent will be f only. You will hear that same frequency, whatever is being generated. But at infinity, your theta will be tending to zero. So it feels like the velocity is completely towards you. So you get maximum frequency. The velocity is pointed towards you, c by c minus v into f. On the other side, when you're leaving, yeah, your velocity is increasing, but there is a problem. It is increasing away from you. So the component is v cos theta going away from you. If you're going away from you, the frequency will drop. So at infinity, at plus infinity, the velocity is completely away from you. You will get minimum frequency, which is c by c plus v into f. So we can clearly see here maximum, normal frequency, minimum frequency. The frequency is always decreasing. Now, if you try to plot a graph, this is f max, and this is f, and this is f minimum. So your graph will start here at f max and decreases, touches f, and then decreases. The graph will always decrease. So at any instant here, the frequency will be c by c minus v cos theta. C by v cos theta. So there, have a look at the graph. So the answer is that the frequency is always decreasing. This is that sound that you're hearing in that F1 racing car, right? You know, when the cars are coming towards you, you have a high frequency, and as they leave, the frequency drops. So you get that sound like, when that F1 cars go, you must have heard that sound. You get a high frequency and then it just nags. Clear with this? So F apparent always decreases. Good theoretical question. If they don't ask you a graph, they'll ask you this. Let's see one more. Top view. We have a circular track. We have an observer here. This distance is r. Circle cut radius is also r. We have a frequency f, and this guy is going with you. So the source is going in a circle. Observer is just standing there. Find the time interval between maximum and minimum frequency. Find time interval between max and minimum frequency. I can even ask you find time interval between minimum and maximum frequency. Both are not same. This also roughly approximately can try to put a graph. It looks weird, but let's get this thing. So in this question, right, the time interval between maximum to minimum and minimum to maximum is not same. Let's see how you do this. This is another standard question. Let's see. Now here the most common mistake, right? What people think is, oh, when it is here you get minimum, when you get here maximum. Again, be careful. It depends on the velocity towards you. So now what we need to look at here is where is this? Yeah. So when do you hear maximum? When the velocity is completely towards you. So basically that will be when you form a tangent. So from this guy, if you draw a tangent, that is not the topmost point. The velocity is away from you. At this point, you'll hear minimum frequency, which is c by c plus v into f. Similarly, if I draw one more tangent here, at this point, the velocity is completely towards you. Here you'll hear maximum frequency, c by c minus v into f. You can clearly see this distance is 2r and that is r. So this is 60 and this is 60. This is why I said the time interval between maximum minimum and minimum maximum is different. So he is asking between maximum and minimum. So time interval between maximum to minimum, you have to travel 120 degrees. So that is 1/3 of 2 pi r by u. But if they ask you time interval between minimum to maximum, that would be 2/3. So it's not a symmetrical thing. And what about these points here? When you're exactly at this point here, you can clearly see the velocity is 90 degree. You will hear f apparent is f only. And again, when you're here exactly here, f apparent is f. Clear with this? So the tangent, so that is a catch there. It's not the topmost and the bottommost point. Now let's see one more. X and Y axis. We have a source here of frequency f going with speed u. This is at d comma 0. We have an observer who is also going with speed u. His coordinates are 0 comma d. This is the scenario at t0. Find the frequency heard by the observer when the source is at the origin. C is the speed of sound. This is a good question, right? Find the frequency heard by observer when source is at origin. Yeah, they can ask f app as function of theta. Let's see how you do this. They have same speed. They're initially at the same distance from origin. Be careful with that question. It looks innocent. It's not. Hmm. In case you're wondering, listen to this. Let me ask you another question. Find the frequency heard by the observer due to the sound released by the source at the origin. Look at the question. Look at this question. Find the frequency heard by the observer when the source is at the origin. They're completely two different things. Find the frequency heard by the observer due to the sound released by the source at origin. That's a different question. And this is a different question. Think, I'll give 2-3 minutes. It's a good one. Most people will think it is that case. So Right idea. Let's see. Let's see. So what was the trap here? नहीं रे आदित्य. So listen carefully. The thing was, let me draw the picture. Let's say the source was here initially. This is T0. Let's say this is time T1. This is when the sound was released. This is time T2 when you reach the origin. Look at this guy. You're here at T0. You're here at somewhere T1. And finally, you're here somewhere here at T2. Now, remember, what did I say? You should take the source when the sound is released and the observer when the sound is being received. That means you should take this line. You need the source ka position at T1 and observer ka position at T2. So this guy is actually listening to this sound. By the time this sound reaches from the source to the observer, the source has reached the origin. So the sound was not released at the origin. Is this making sense, everyone? As the source is traveling from initial position to the origin, somewhere in the middle, it released a sound. By the time this sound is gone to the observer, you have completed the distance and reached the origin. So the sound which was released at the origin, you will never hear that. That will take time. So we need to find velocities in this direction. So if this was u, this was theta. This guy velocity was u, and this was 90 minus theta. So now when you take the components, F apparent will be C. The observer is trying to run away from you, u cos 90 minus theta. The source is trying to come towards you, minus u cos theta into F, which is C minus u sine theta by C minus u cos theta into F. Now, how do you find theta? That is an interesting one. Now look at this. That means from here to here, the time interval is t1 minus t2. So that will be u into t2 minus t1. So the source must have traveled a distance of u into t2 minus t1 when it is going from here to here. At the same time, the sound also is traveling this diagonal distance, which is speed of sound into t2 minus t1. Is that making sense? The time taken for the sound to go from this distance along the diagonal must be equal to the time taken for the source to go from t1 to origin. And from here, you can clearly see cos theta will be the adjacent side, which is u into t2 minus t1 by c into t2 minus t1. So you don't actually need the times. You get cos theta u by c. Is that logic making sense? The source is traveling with speed u from t1 to t2. So what the distance traveled is? Speed of source into t2 minus t1. At the same time, the sound is traveling along this diagonal. What is the time interval? T2 minus T1. The time is still the same. The speeds are different. So from there, we get the distances ka ratio and we can finish it off. All clear with this? So now it is doable. Like you substitute there and you'll get an answer. Any doubts on this? All clear with this? There, that's a bit about Doppler. With that, we are done with waves. So next, we will start off with wave optics. Take a break, come back by 9:45. We'll continue from here. Yeah, let's start off. Now, listen carefully. So, wave optics. First, we'll see what it is about. So, in ray optics, we dealt with the particle nature of light. To which we explained phenomena like reflection, diffraction, and formation of images. But there are other phenomena. There are certain phenomena like interference, diffraction, polarization. These things, right? You cannot explain with ray optics. So the story goes like this. So the first guy who tried to explain what is light was Newton. Meaning, at least that's officially the thing. So he came up with a theory called the corpuscular theory. In that, he assumed light is made of particles called corpuscles. They have different sizes, and because of the different size, you get different colors. And he explained the whole thing, and it did explain reflection, and he did assume few wrong things, and he explained refraction also. Then everything was done. And that theory was almost, people accepted it almost for 150 years. Uh, and first of all, right, it was Newton. So someone came up with a new theory. People used to be scared. People used to make like how dare you can go against Newton types. It always happens, there's always a hierarchy. No matter how much people say, right, science science wins and all, it's all bullshit. End of the day, there is always a politics, no matter what you do. Whether you're doing a corporate job, whether you're doing research, there is always uh, that always happens. There is always this politics that goes on. I mean, simple thing, right? Tomorrow, if you're doing research under a researcher and you found out in your research that what your teacher was teaching you was wrong, do you think you will accept it so easily? Meaning his entire life work of 20, 30 years, you just proved it in 2 years, it is wrong. That guy is just going to go mad. So you have to be careful. So then people did realize, something is wrong with Newton's theory, but they didn't know what. Then comes a guy called Maxwell. Actually, there is a guy called Huygens, and then Maxwell is the main guy. So Young's Maxwell. So you must have heard that guy in magnetism and everywhere. So we'll see later on Maxwell equations. Okay. So this guy comes up with an experiment and he shows them. That's why we call it an Young's double slit experiment. YDSC. We have it later on. And in that experiment, he clearly proves, the only way this experiment result would have happened if it was a wave, right? Particles won't create such kind of phenomena. So we will see what it is. See, it is always like that in science. Think of your chemistry, J.J. Thomson model, watermelon model. Initially, people thought the nucleus is like a watermelon and the electrons are placed inside the nucleus. Right? And then Rutherford came and said, no, let's do an experiment. So see, Rutherford didn't know. Rutherford said, okay, let this be the model. So let me take some alpha particles and bombard them. So what Rutherford expected was this. Rutherford thought, since the charge is distributed, these alpha particles are so strong, they will just pass through them. But because these are positive, you will find alpha particles will have slight deflections, meaning all the alpha particles will pass through and they will all deflect. They'll all will deflect. But after the experiment, what they saw was something else. They saw most of the particles went undeflected, and a few particles which got deflected, they had huge deflections. So the theory was saying something, but your experiment is showing something, and then you say, okay, maybe somewhere there is a wrong. And then Rutherford came up with an idea, okay, maybe the entire nucleus is placed at one place and then the electrons are going around, just like a planetary model. And then Bohr comes and says, no, boss, in your planetary model, there is a problem. If the charged particle is accelerating, it emits photons and it collapses. So you cannot have electron in any orbit. So he comes and says there are stationary orbits. Then comes this guy, I think, who is the Sommerfeld, and says, no, these are not circular orbits, these are elliptical orbits. And then comes Schrodinger. Schrodinger says, no, there is no electron only. It is a cloud wave function. That psi and everything. If you see, that's what the theory just keeps evolving. So then comes Maxwell, and then he proves, boss, this light is a wave. Then all people accepted, oh, light is a wave, light is a wave. Then comes Einstein, 1907, 1910. Einstein, brings his photoelectric effect. And he proves the photoelectric effect can happen only if light was a particle. And Young's Maxwell proves the phenomena can happen if light was a wave. At this point, people were confused. They didn't understand what it is. And then they said, fine, light has a dual nature. What this means is we have no idea what the hell it is. So let's call it dual nature and just keep our mouth shut. So people they all accepted it's called dual nature. So depending on the phenomena, sometimes light becomes like a wave, sometimes it becomes like a particle. We are still trying to figure it out, right? So yeah, that is the thing. So for now, because see, in science, you cannot have two different things for the same. You can't have two theories for the same thing. You should be able to explain everything with one. So there is something called theory of everything. They're working from last 40 years, progressing slowly. So, but anyway, so what is this particle nature and what is wave nature? So let's be very clear with this. I'll give you a crude example, but this idea is important. When I was in school, right, when someone used to say wave nature, what I used to think? Anything that goes like this is a wave. Right? That's a bullshit definition. Matlab, just imagine, if you ever seen a snake going, snake also goes like this, right? So snake is a wave. No, right? So anything that goes like this is a wave is a bullshit definition. So what is exactly a wave nature and why that word came? So let me tell you first of all, what is particle nature? When do you say something is behaving like a particle? You should think like that. So when you say something is behaving like a particle nature, like I said again, a crude example, a simple thing, 1 plus 1 is 2. It is so obvious, we never think it is like, okay, it can be anything else. So if I throw one particle here, I'll see 2 here. If I throw one particle, 2 here, 2 here, 2 here. It looks obvious. So 1 plus 1 is 2. Now be careful when I say 1, remember these are not numbers. Think of like this, a property plus a property is 2 times the property. The property can be mass, it can be energy, right? It can be things like that. So 1 kg plus 1 kg is 2 kg. So here 1 is not a number, it is like a property. Example, we say like 1 joule plus 1 joule is 2 joules. Or 1 m plus 1 m is 2 m. Just for your understanding, to keep it simple. What is a wave nature? People observed in nature, sometimes 1 plus 1 is not 2. Instead of particles, if you send a wave, so people have observed, right, this thing happening in waves. If you send a wave and you send a wave, sometimes you'll see 0, sometimes you'll see 4. You can see anywhere between 0 to 4. So in a wave nature, 1 plus 1 is between 4 and 0. Again, like I said, remember, it is not a number, it is a property plus a property. Can be anywhere between 4 times the property between 0. Let me show you an example. Consider two waves. We have studied waves already. So if you're sending a wave plus a wave like this, two waves, superposition. So this was amplitude A. This was amplitude A. This thing has intensity I and intensity I. When these two waves add up, you get a bigger wave of amplitude 2A. And we know intensity is proportional to amplitude square. So this wave amplitude will be 4i, intensity will be 4i. Means if you add two waves of intensity I plus I, you'll get 4i. Or I can do like this also. Suppose if you added this and if you added this. Here, if you add two waves of intensity I and intensity I, you will get flat. Here, the intensity becomes 0. Did you see here? So when you add the intensity I plus I, sometimes you can see 4i, sometimes you will see 0, sometimes you'll see anything in the middle. This is the property of a wave. Waves behave like this. And energy still comes out, okay? The energy is still comes out. Think of like this. Matlab, I'm sending 2, 2, 2, 2. That is 8. This is still 8. Energy is not, there's no problem with energy conservation. It is redistributed. It is being distributed in such a way, some places have more and some places have less. Right? And like I said, this is just a crude example, Rutsa, not exactly a definition, just for your understanding. So people observed waves behave like this. Then they said, anyone who has this kind of a property, we say they have wave nature. Understand the meaning of that wave nature. And later on, we will see in an experiment. What people saw, right, was this. Meaning when you throw electrons at very high speed, let's say you're throwing a lot of electrons at very high speed, this is what they observed. Sometimes you'll see 4 electrons, sometimes you'll see 0 electrons. The electrons are behaving as if they're a wave. That's why we will say electrons have wave nature. Do you get the meaning of it? It doesn't mean electrons suddenly started going like a sine wave or something. I used to think like that when I was in 11th. The electron started going in a curve, so it became a sine wave. That means when a particle is thrown in the air, projectile motion is not a wave. Meaning, if these are snakes, means when you throw one snake plus one snake, sometimes you'll get 4 snakes, or sometimes one snake plus one snake, you'll get 0 snakes. So snake is a wave. You're getting the point? So far in nature, we have seen only these two things. 1 plus 1 is 2, or 1 plus 1 is 0 to 4. Whenever something behaves 1 plus 1 is 2, we call it as a particle nature. Anything that behaves 1 plus 1 is 0 to 4, we call it as a wave nature. So tomorrow in an experiment, if I'm using protons, and for some reason, whatever is the reason now, we really don't know why it happens. This is a quantum phenomena. They just get redistributed. At some places, you will get 0 protons, and sometimes you'll get 4 protons. You can get any number between 0 to 4, right? So then we say the protons are behaving like waves. That is the meaning of it. They have wave nature. This understanding is clear. So tomorrow anyone says particle nature, wave nature, just remember this. Not exactly anything to do with the thing, but you should have an idea what is particle nature, what is wave nature. Tomorrow, if you find something where 1 plus 1 is between 8 to 0, maybe if you find something like this is the third type of nature. Then we will call a different name for this. So far, we have not seen anything else other than these two. Everything gets classified either into a particle or a wave nature. So this light, in some cases, it behaves like 1 plus 1 is 2. Some cases, it behaves like 0 to 4. That's why it is so confusing. So people gave up and said, boss, it has dual nature. I'll give a simple example. Think about this. Let's say you're standing here and looking at the sun. Now ask yourself, if light was a particle, that means sun is emitting a bunch of photons. That means if I go really far, very, very far, and if I stand at some place, there is a possibility 2 photons will just pass like this, isn't it? If sun is simply emitting bunch of photons, if I can go and stand really far, I will find a position where the 2 photons are just passing away from me. That means whoever is standing here cannot see the sun. But if I stand here, I can see the sun. You getting the problem? So if light was a particle, this should have happened, meaning there will be some positions where you can see the sun, some positions you can't see the sun, but we don't see this. That means light is a wave. So when you say light is a wave, that means now it is being transmitted, something like a disturbance in the region. Now everyone can see the sun. So that means when sun is traveling from in the space, it is a wave. But if you put a photoelectric plate, solar cell, the moment the light wave comes and hits a solar cell, for some reason, it becomes particles, the photons, and they start hitting the solar cell, and you get the electrons out. Meaning it's all confusing. No one knows why the hell it is like that. Meaning suddenly the wave becomes a particle. So it is like depending on the experiment, it will behave however it wants. So we'll not get too much into it, but keep that much in mind. So it's still work under progress. Now, the first guy who tried to say something about the wave is the Huygens wave theory. So there's a guy called Huygens. He came up with some ideas there. He was quite inspired by the water waves, throwing stones into the water. Then a wave theory of light. Again, just a theory there. Huygens wave theory. So he said this entire space is filled with a medium called ether. So ether is that imaginary medium which prevails in space in isotropic, perfectly elastic and massless medium. So he thought, just like the waves travel on a water wave, he said this light is traveling through space through this ether cum medium. Unfortunately, we have never found this medium. There was every experiment has failed to prove there is any medium there. Yeah, but that is the thing. So there are multiple mistakes with this. But the important thing in this theory, right? He did come up with something interesting. He said all these particles which are vibrating in same phase, it's called a wavefront. So think of the wave in a beach. When the wave is coming towards you, that wave which you see, right, that whole thing is called a wave front. So the whole thing is coming up like that. Light travels in the medium in the form of a wavefront. When light travels in a medium, then the particles of a medium start vibrating. So, yeah, like I said, we never found these particles. Later on, we figured out light is actually an electromagnetic wave. So there are no particles, there are electric and magnetic field fluctuations. Then this is the idea he came up with. He said when the light is coming, every point on the wavefront will act like a new source. Every point on the wavefront becomes a secondary source. And these secondary sources will generate a new waves, right? And that will generate another wave and so on. So he came up with that idea like, every point on the wavefront will generate new waves and so on. This is how it will keep on propagating. Like I said, it's all just theory there. So this is a spherical wavefront. You can just go through this, just read it. I'll give you some 30-40 seconds. Just go through this also. Let's see. And with this theory, right, he could actually explain stuff, and that's why it did become a little interesting. It could explain everything that the light did and the particle nature did, and it could explain even more. Yeah, but again, it had its own problems. It explained reflection, refraction, interference, diffraction, polarization. rectilinear propagation of light, everything, but it couldn't explain photoelectric effect, Compton effect, and Raman effect. So these all are based on particle nature. So this will be good theoretical questions in CET. Which of the following, phenomena can be explained by particle nature of light? This is where people started going mad. They didn't understand like what is light exactly. It is a particle or a wave. It is explaining something, but it's not explaining something else. Like I said, the whole thing, this definition is the most important one, the definition of a wavefront. Now for these wavefronts, right? Depending on what kind of source you have different wavefronts. So if you're having a point source, the sound will travel in the form of a sphere. We get a spherical wavefronts. If you have a line source, we get a cylindrical wavefront. We have done something like this in this question, if you remember, decibels. Remember this question? Sound is traveling in a point source, sound is traveling in a cylindrical wavefront. The intensity is I is proportional to 1 by r square, 1 by r. It is the same story. This is actually taken from there. So this is how the equation should look for a spherical wavefront. The equation will look like this. Y is equal to, the amplitude becomes 1 by r because I is proportional to 1 by r square. So this would be something like A naught by small r sine kr minus omega t. So for a point source, the wave amplitude will decrease with distance. The more you travel, the more it will decrease. For a cylindrical wave, it will be A by root r. So the amplitude changes with distance. So what we have been studying so far is a plane wave. In a plane wave, the amplitude doesn't change. So your wave equation will change depending on what kind of source you are using. The backward propagation is this. When you said, right, in a wave front, every point is acting like a source. Huygens assumed what he said, the waves are going front. And then he said, we will join these things again. We got a new wave front, and again, these will generate new waves and so on. Then the question comes, if the wave is going front, if this is a point source, why is it not generating waves behind also? That's called backward propagation. So he couldn't explain this, but mathematically, if you actually calculate, we can prove they will all cancel out, but we'll not get into that. That's the meaning of backward propagation. If you say every point is a point source, why should light go ahead only? Why can't it come back? Clear? So I'll just summarize this whole thing. This is just a story, everyone, like important for boards. And you should just have an idea of what it is, wavefront and everything. There, these are the main important points. Just read this. So again, the normal to the wave fronts represent the ray of light. So a line drawn at right angles to the wavefront is defined as ray of light. Meaning, suppose if you say these are wavefronts. So how is the light propagating here? Light is propagating like this. The green ones are the light rays, so these angles are perpendicular. You can think of like them electric field and equipotential surfaces. So the green ones are the propagation of light and the red ones are the wavefronts. So think of the wave in a beach. Ever seen the wave, the wave in a beach? The wave is perpendicular, but it is coming towards you. So the wave is traveling forward. So this is the direction of light, but this curve here is your wavefront. That idea is important. Just please read through these points. All theory there. So in this whole story that I taught you, remember the main thing you need to remember is these two. What is a wavefront? All the particles in phase. What is the direction of light rays? perpendicular to the wavefront, if you draw a line, that will be the direction of the light ray. These are the two main important things. Yeah. Let me show you how they'll train questions on this. You get some good questions on this. Let me show you one. They will say like this. They will say we have a biconvex lens. Then they will say you're sending wavefronts like this. So these are plane wavefronts. Then the question will be, if you send plane wavefronts into a lens, what kind of wavefronts will come from the other side? And let me give you a little more information. Let's keep it simple. Now, how to do these kind of questions? Listen. So this is what you do. So this is a lens. So the wavefronts are plane wavefronts, perpendicular lines to it. So the green lines will be your light rays. So you should always draw your light rays. So when you send light rays parallel to the lens, they meet at the focus. Now draw the wavefronts again. Now again, how do you draw a wavefront for these things? They should be perpendicular to it. Perpendicular, perpendicular, and perpendicular. Means if you send plane wavefronts through this, you will get wavefronts which are converging. This is how it will look. You're getting the shape, everyone? If you send a plane wavefronts, you'll get a converging wavefronts. This is how you draw. Everyone clear with this? Let me ask you one more. Now you guys try to draw. Same thing. Suppose if I give you a diverging lens. Again, if I give you plane wavefronts, what will come out from that side? How will it look like? Suppose if I give a prism, and if I give you plane wavefront, then what will come out from the other side? Suppose if you have a convex mirror. If you send again plane wavefronts here, what will you see here? You need to draw the shape, how it will look. I'll draw the prism in the next page. Again, see, this is how you draw. So take this by thing. So if you send parallel rays, they will diverge. So first you always convert this into light rays and then you draw them. So this is the plane wavefronts. And look at these wavefronts here. They're diverging and they're becoming bigger. So if you send plane wavefronts here, they will come out like this. Is this making sense, everyone? How to draw? Now, can you draw for the convex mirror? So this is based on wavefronts and ray optics. So idea is the same. Let's see. Again, let's draw the picture here. So if you send parallel light rays here, they would bounce off like this. So if you send parallel wavefront, they would come out like this. So this will go and these will come out. Again, diverging wavefronts. I hope you're getting the idea there. So let's say we have a prism. If I send these, what will come out? So let's say this is mu1 and this is mu2. Medium is different on both the sides. Mu1 is greater than mu2. Now, if I send wavefronts here, then what will come from the other side? If you have a plane mirror, if you send these, then what will come after reflection? And if you send plane wavefronts through this, what will happen? Get these 4 questions. That's mostly array optics questions, basically, but you're just calling it wavefronts now. Get them all. I'll give you a minute or two. Let's see. See. So if you send a light ray through a prism, remember it will deviate. So you will get the wavefronts will become like this and they'll come out like this. Remember the deviation delta is a into mu minus 1, something of that sort. Same thing here. When the light ray goes here, this is the normal. The green ones are the light rays. Mu1 is greater than mu2, so you're going from denser to rarer. So when you go from denser to rarer, there's even a chance of TIR. Let's assume it is not happening. You should get away from the normal. So the green guy will go away like this. So yeah, if it is more than critical angle, there'll be even a reflection. In a plane mirror, so if you send a light ray like this and it goes like this, so basically this was the object, this was the image. So the light ray should converge here. So this is how it will look. So after hitting here, this is how they'll become. So they're converging here. So the light rays are going like this, they're hitting and they're all converging here. So they will compress. This, if you send light rays, they would meet here at 2f. Then they would become again parallel because both are focus. It will be at the common focus. We have done this kind of equation in ray optics. So the light rays would become like this. They'll meet here and then again they'll converge and then they'll become parallel again. Look at the G equation. It is a good one. That is how the wavefronts will behave. Plane will come, they'll converge, they'll diverge, and they'll become plane again. But diffraction we'll see later on. Let's learn one thing, Nare. Let's not mix up everything. This dotted line, there is something here. You're sending this and wait, I think in a plane mirror. Wait, I did something wrong. It's a mistake actually. The image will be here, na? My mistake. So it will feel like the rays are coming this way. That was a mistake, everyone. Image is that side. It feels like rays are coming from that point. If I did wrong. So you sent these wavefronts. They hit something here. We don't know what is there. But after hitting here, they become like this. So then the last question is this. Then what is placed here? Options will be convex mirror, convex lens, biconvex lens, and biconcave lens and all that stuff. This is your incident wavefront. So you're sending this and these are coming out. So what kind of a system will give you these kind of wavefronts? Concave what? Right, Samit. Right, Arya. नहीं पढ़ा. Let's see. So this, right, is a concave mirror. Because think of like this. So object is here and the image is here. This is the thing. That's why that was wrong. How can you get an object and image here? First of all, the rays are coming back. This is not a lens. Because in a lens, rays will always keep going forward. Right? This can't be a plane mirror because just now I said it should be somewhere here. And here, if it is converging here, a convex mirror will never create a real image. So this has to be concave mirror. That's the possibility there. So object is here. The image is here. So the wavefronts are coming from here and they're getting converged here. Something like this is happening. So they can ask questions like this also. That's a bit about wavefronts. Clear with this? Next thing, coherent sources. So what are coherent sources? two sources are said to be coherent if they have same frequency and a constant phase difference. Amplitude can be anything. So this word is important. A constant phase difference. Remember that angle phi? It is like that. Now, a few things here. If you take two independent light sources, meaning if you take two bulbs identical in every aspect, molecule to molecule also, if they're same, they can never be coherent. Two independent light sources can never be coherent. The reason, you need to understand how light is produced. Any light, when you put some fire that produces light, or when you switch on a bulb produces light, LED, anything, everything, right? When they produce light, the reason is simple. You're providing energy, the electrons get excited to higher orbits. When they de-excite, you get photons. That is how light is coming. When you are putting a fire is nothing but a heated up gas. When the gas gets heated up, they collide with each other. The electrons are getting excited to higher orbits. When they de-excite, you get that color. Bulbs may the same thing happens. Now, if the light is because of excitation and de-excitation of electrons, this is completely random process. If you have even two identical bulbs, there is no guarantee they will produce light in the same way every instant. That is the reason two bulbs, even though they're exactly identical, they will produce different kind of light at every instant. Yeah, on an average, they'll produce same, but every instant, not same. So light is produced due to excitation and de-excitation of electrons. Which is a random process. Therefore, two light sources will never be coherent. Basically, they'll never be in sync. So if you have a bulb here, let's say this is producing y is equal to a sine kx minus omega t plus phi 1. You have an identical bulb, but let's say this is giving y2. This would be phi 2. So frequency is same, amplitude is same, but the problem here is the phase angles phi 1 and phi 2, they change with time. They themselves are not constant. They keep on changing every instant because the same bulb, the light it produces now is not the same light it will produce after next moment. So the bulb itself is messed up. Like it doesn't even produce the same light every instant. And how can you say two different bulbs will be in sync? Therefore, the phase angle phi 2 minus phi 1 will also vary with time. So they can never be in sync. Then how do we create coherent sources? Since you can't have two independent sources, we have to create them from a single source. We can create coherent sources by creating them from a single source. This is what we do. This is the most common thing. Let's say we take a slab and cardboard, and we make two rectangular slits. Now, when you send light through this, the light which comes out from here, now the two slits will behave like two light sources. We make two thin holes on the cardboard. Since they're coming from the light source, they will be in sync. S1, S2 are coherent. So you need to create sources like that. Or you can even do this thing. If you take a lens and if you say this is mu1 and this is mu2, and if you have an object here, we have done this in ray optics, so this will create one image I1. This will create a second image I2. These are coherent. Or you can even use a mirror. The light source, when it bounces and goes off here, the image S and I are coherent. So there are multiple ways to do this. Or you can take a biprism. So it's a two prisms stuck to each other. And when you put a light source here, the light rays which are going up here, they would go something like this. That will be like one image. The light rays which are going at the bottom, they would go like this. That will create a second image. I1 and I2 are coherent. So somehow we need to split that light and create two images. So there are multiple ways to do this, but these are a few examples. Clear with this? So then that's a bit of an introduction on wave optics today. One is the wavefronts and this is the coherent sources. So next class when we catch up on next Tuesday, we'll continue from here. The next class will be quite important. I will be teaching you the main part of something called interference. Next class is all that main theory there. Not tough, but once you understood this, that will be the crux of the whole chapter, right? It's not a big chapter. Mostly we should be finishing off this in another 3 classes max. So okay, with that we'll wrap up for the day. Like I said, waves is completely done. So please start solving. Don't delay it anymore. Because wave optics you can start doing from next Thursday. So this also will be almost done next Thursday. A little might spill over. So you have a lot of work to do. Okay, with that we'll wrap up for the day. I'll see you guys again on Tuesday. So any doubts, anything else, please stay back and ask. Also, you're free to leave. So take care, stay safe.